to Rise Learning Machines seminars, everybody. Today, we have a visitor from Lund University, Martin Trimmel. He's a PhD candidate at Lund University. He has his master's from the University of Cambridge and his bachelor's from University of Edinburgh, where he's been focusing on mathematics, algebraic geometry during his undergraduate studies. Martin does his research in mathematics, using mathematics to obtain better theoretical understanding of deep learning, and also on the effect of activation functions on the network function and its performance. The topic today is linear regions of deep neural networks, an analysis of the expressivity of deep convolutional neural networks. And this is based on work that was presented at ICARE 2021.
Thank you very much for the introduction. My talk consists of 5 parts. In the first part, I will give you an introduction to linear regions and neural networks. Then I'll cover some background on tropical algebra. Next, I'll explain our algorithm for extracting linear terms from neural networks. Then I'll move on to some of our experiments. And finally, I'll present some ideas for future work. So let's start with the introduction. The rectified linear unit, ReLU, is one of the most widely used activations in modern deep learning. It's particularly popular in CNNs and used, for example, in VGGs, Google Nets, and ResNets. The ReLU activation is defined as ReLU of x is equal to maximum of x and 0. This means that ReLU of x is equal to x when it's positive, and ReLU of x is equal to 0 when x is negative. When the value of a node is positive, we say that it is activated. Otherwise, we say it's inactive. Activated nodes correspond to information flowing through the network, and inactive nodes correspond to no information flow. Finally, we can think of the activation pattern of the network as a long binary vector consisting of ones and zeros. There is a 1 for each activated node and a 0 for each inactive node. Let's now visualize what I've just said. Imagine a simple neural network classifying images into 2 classes, cats and dogs. All of the activations in this network are ReLUs. When we take an image and pass it through the network, some of the nodes get activated and others not. For a fixed activation pattern, the network is a simple linear function. When we take a different image and pass it through the network, different nodes get activated, leading to a different linear function. The images are points in a high-dimensional space, which we represent by a 2D plane here. The activation patterns partition the space into linear regions. The network is a simple linear function on each of these regions. When we move around in the input space and cross one of these boundaries, an activated node becomes inactive, or an inactive one becomes active. Hence, the activation pattern changes, and the network function is a different linear function. Intuitively, the more linear regions a network has, the higher is its expressivity. Hence, a network with a large number of linear regions should be better able to adapt to different datasets. previous work has focused on measuring this expressivity by counting the number of linear regions. However, there are some problems with this approach. Even for very small networks, the number of linear regions exceeds the number of atoms in the universe. On the other hand, only a tiny fraction of the regions contain training data. So this raises the question, how does the network use the information from training regions to generalize to unseen data? To study this issue, we've derived an algorithm called TROPEX, which allows us to extract only those linear regions associated with training data. The resulting reduced function has only as many linear regions as data points in the dataset. So for example, for MNIST, that's 60,000, and for CIFA10, 50,000. So it turns out that ReLU networks can be analyzed using tropical algebra. Before explaining our method, I will therefore need to introduce some basic tropical algebra notation. In a tropical algebra, there are two operations called tropical addition and tropical multiplication. Tropical addition replaces ordinary addition, and tropical multiplication replaces ordinary multiplication. The tropical sum of two numbers is the same as their maximum. Hence, the tropical sum of 2 and 3 is the maximum of 2 and 3, which is 3. The tropical product of two numbers is the same as the ordinary sum. Hence, the tropical product of 2 and 3 is 2 plus 3, which is equal to 5. The tropical power of two numbers is the same as their ordinary product. Hence, 2 to the tropical power of 3 is the same as 2 times 3, which is equal to 6. This gives rise to an algebraic structure called the tropical semi-ring. The tropical semi-ring consists of the real numbers with negative infinity and the tropical addition and multiplication operations. This structure is a semi-ring and not an algebraic ring because the tropical sum has no inverse operations. And already here, you may see some similarity to how ReLU networks are built up, because in these ReLU networks, you've also got the maximum of a number and 0. You've also got additions, and you've also got multiplications. So intuitively, we can already see here that there is some similarity happening. Now, you're also probably wondering, what is so tropical about these operations? Why is tropical algebra called tropical algebra? The reason for this is that one of the pioneers in the field was a Brazilian mathematician, and later French mathematicians said that he worked on tropical algebra and tropical geometry because he was from Brazil. So that's the reason behind the naming of the field. And it has nothing to do with these operations being very exotic or difficult to understand. And in a similar way, we can also define tropical functions. A tropical monomial is the tropical product of factors taken to some tropical power. This is the same thing as an affine function, i.e. a linear function plus a constant. So this is the same as these linear terms that I've mentioned previously. A tropical polynomial is the tropical sum of multiple tropical monomials. This is the same as the maximum of multiple affine functions. A tropical rational function is the tropical quotient of tropical polynomials. And that's the same as the difference of the maxima of affine functions. And finally, a tropical rational map is a multidimensional function where each entry is given by a tropical rational function. Interestingly, tropical rational maps are the same as ReLU networks. It has been previously shown that every ReLU network is a tropical rational map, and conversely, every tropical rational map can be represented by a ReLU network. Using ordinary non-tropical notation, each output dimension is a difference of maxima of affine functions. Our algorithm TropX extracts exactly those linear functions on which the training samples are maximal. It would be impossible to extract all of these affine functions that you can see in this representation here, because as I mentioned previously, the number of linear terms, linear regions in a neural network, even for very small network, is larger than the number of atoms in the universe. So this complete expression here for a network has more terms than atoms in the universe. And yes, and then the derivation of the TropX algorithm relies heavily on the use of tropical algebra. Now I'm explaining the main part of our algorithm. Here you can see a visualization of our algorithm. The input to the algorithm is a neural network, a trained neural network, and a set of labeled data points. The output, which you can see in the lower right corner, is the extracted tropical function. TropX starts with the last network layer here on the left. The weight matrix is split into its positive and negative part. The label of a data point determines which matrix row grows to extract from the positive and negative part to form the first tropical function. The algorithm iteratively merges the other layers into tropical functions, computing the compositions of several layers. For activation layers, like here, entries in the tropical function are set to 0 according to the activation patterns. For linear layers, the tropical function gets multiplied by the weight matrix. And this is just a simplified visualization of the algorithm. And in general, the algorithm can handle convolutional layers, batch normalization, max pooling layers, also leaky ReLU or parametric ReLU. So in general, any piecewise linear neural network. And then after this type of iterative merging procedure is done, and all layers have been merged, the output is the tropical function. And here I'm showing our main theorem, and as a simplified version, if we're given a ReLU neural network and a set of data points, TropX extracts the corresponding linear terms. And our main theoretical result says that the linear terms are indeed extracted from a tropical representation of the network, and that the resulting function, the resulting tropical function, agrees with the original network on neighborhoods of all the data points used by the algorithm. So next, I'm I'll be presenting some of our experiments. And before I present the experiments, I would just quickly want to remind you that we start with in the algorithm, we start with a network with more linear regions than atoms in the universe. And then after extraction, our network has one linear region for each data point. That's 50,000 on the C10 dataset and 60,000 on MNIST. And then after extraction, all test samples there on some linear region of the on the same linear region as training samples, as these training samples are used during the extraction process. So at first, we started by investigating how training and test samples are distributed over linear regions of the neural network. Since all of the extracted linear terms are different for both training and test samples, I was a bit behind. Yeah, we are looking at linear terms of training and test regions, and then we found out that for both training and test samples, all points lie on different linear regions. This is not a result of overfitting during training. All data points also occupy different regions when we check the linear regions after, for example, 1, 3, 5, 10, 15, and so on epochs of training. And so this phenomenon is not due to overfitting. And therefore, this means that generalization of neural networks cannot be explained by test samples falling into the same linear regions as the training samples. Or in other words, by it cannot be explained by test samples inducing the same activation patterns as training samples. This means that test and training samples always have different activation patterns. So from this, we can conclude that that test samples fall into different regions than training samples, but it might still be possible that neighboring regions are nearly identical and that test samples fall into such neighboring regions of training samples. For this reason, we tested the similarity of the linear regions of test samples before and after reduction. We take a test sample and extract the linear coefficient of its linear region in both the original network and in the extracted function. For these linear coefficient vectors, we calculate the angle and the Euclidean norm difference. The plots here show both values for all test samples. So each point that you can see here corresponds to one test sample. And we differentiate between test points that get correctly classified by the extracted function and those that were incorrectly classified. So the correctly classified ones, they are in blue, and the incorrectly classified ones, they're in red. So here we see a clear difference between CNNs and FCNs. FCNs meaning fully connected networks. For CNNs, the coefficient vectors of both training and test affine function are all close to orthogonal for correctly as well as incorrectly classified points. For fully connected networks, the angle and distance of correctly classified points are smaller than for incorrectly classified ones. But they're still far away from zero. And this therefore rules out the possibility of test samples falling into very similar neighboring regions. Finally, instead of comparing linear coefficients, we also tested the similarity in activation patterns before and after extraction. In each layer, approximately 80% of neuron activations agree between test and training regions. So this shows that also the activation patterns of test samples deviate considerably and generalization cannot be simply explained by very similar activation patterns. So as predicted by our theorem, so now I'm talking about the accuracy of these extracted functions and compare them to the original network and the true label. So as predicted by our theorem, the maximum of the extracted function agrees with the maximum of the original network on all training points for each of our networks. In particular, the network and the extracted function assign the same label to each training data point. To investigate how well So we want to investigate how well the coefficients and of these linear regions generalize to unseen data. We compare the test accuracy of the network and the test accuracy of the extracted function. We see a consistent difference between CNNs and FCNs across both datasets, across both MNIST and CIFAR-10, and across all of the architectures that we use. Here we've used multiple architectures, and here these results are average values. So we see that there is a drastic drop in the test accuracy of the CNNs and a relatively small drop in the test accuracy of fully connected networks. And interestingly, we also see that for MNIST, the extracted tropical function has almost the same test accuracy as the original network. And this is surprising because all known bounds on the number of linear regions of the original network suggest numbers of linear regions in order from 10 to the power of 80 up to 10 to the power of 17,000. And from these linear regions, we only observe 60,000. So that's 10 to the power of 4, 10 to the power of 5 after reduction. Hence, for fully connected networks on a simple task, the coefficients used in training data generalize well to test data. But for complex data, the learned coefficients generalize worse. And this is remarkable because in previous studies of linear regions, such previous studies were often forced to base their experiments on small data sets or small networks for computational reasons. And it seems that a lot of care must be taken when generalizing observations to more complex tasks. Another one of our experiments that I'm showing here is that we visually inspect samples that are correctly classified by the original network, but misclassified by the extracted tropical function. So here I'm showing the samples that the original network is able to correctly generalize to, but for which the reduction of linear regions is hurtful. We show 5 random examples for both a CNN and a fully connected network across the first 5 CIFAR-10 labels. So that's airplane, automobile, bird, cat, and deer. And the first row corresponds to the first row shows the test samples, and the second row shows the training images corresponding to the linear regions in the extracted function falsely activated after extraction. Note that by extracting linear terms, we remove the compositional structure of the network function, and the extracted function must rely on the information encoded in the linear coefficients of linear regions containing training data. Inspecting samples that were correctly classified by the original network, but misclassified by the extraction, can give us insight what generalization capabilities were removed by extraction that is not contained in the linear coefficients. We see that for CNN, the generalization performance of the extracted function seems to rely on color distribution and background. This supports the interpretation that I previously showed, predicting that the removal of structure by extraction leads to increased vulnerability due to spurious correlations for CNNs. In contrast, for fully connected networks, the extracted functions appear to classify images more according to the global shape present. And now a quick summary of our other experiments. In all of our other experiments, we see considerable differences between convolutional and fully connected networks. This suggests that these two network types use linear coefficients differently for generalization. We have the following interpretation for our results. For fully connected networks, coefficient values of linear terms play a strong role in the classification. For CNNs, the classification relies on their architecture so that the coefficients of linear terms play a smaller role. And now at the end, I'd also like to mention some suggestions or some ideas that we had for possible future work in this field. So our first observation was that this type of algorithm could potentially be used regarding adversarial attacks. It was noted previously by other authors that large linear regions add adversarial robustness, and our algorithm Tropex outputs a network function with maximally enlarged linear regions, and therefore it might provide a tool for studying various adversarial attacks. It would also be interesting to see whether adversarial attacks can harm the performance of the extracted function on training data. Another thing that we've thought is that is regarding network pruning. Our experiment showed that when we remove the structure from a network, this causes a significant drop in the test accuracy while keeping the training accuracy unchanged. Now, tropical rational maps are the same as ReLU networks, so it might be possible to obtain a new architecture representing the extracted function. From a perspective of linear regions, Tropex outputs a minimal function that is unchanged on all training data. Since different network architectures can describe the same network function, it remains to understand what additional structure needs to be imposed on the smaller architecture to obtain high test accuracy as well. And this opens a possibility for pruning techniques with unchanged predictions on the data it was trained on. And then finally, about generalization theory. So previous authors have noted that deep neural networks can learn data perfectly, so they can overfit to random labels. And this results in a network function that correctly classifies any training sample. For such type of over-parameterized models, other researchers studied the performance on test data from a viewpoint of interpolation. our extracted function agrees with the original network on all training data points. Hence, the difference in generalization in how these two networks generalize must depend on how they interpolate between the training data points. So we observe consistent differences between CNNs and FCNs, and this should suggest that the architecture plays a larger role in this interpolation process. We think that if we have further and more tailored experiments with tropics, this could give more insight on the connection between the network architecture and the interpolation performance, and this could support the derivation of bounds on the generalization error for neural networks. So this was everything from me from my presentation. We've got more details on the experiments in our paper, and our code is open source and available on GitHub, so you can also check that out if you're interested. And yeah, I'd like to thank you very much for your attention, and then hand the word back to Olaf.
Thank you for the talk. Do we have some questions for Martin?
I have a question. First of all, thank you very much for a very interesting presentation.
Thank you.
So I wonder about this field of tropical algebra, which sounds very interesting. I wonder, do you know about, are there results for high dimensional algebra? Because in traditional algebra, there are lots of interesting things happen in high dimensions. So I guess that might be interesting also for tropical algebra.
So what do you mean with high dimensional algebra as opposed to tropical algebra?
So if there are, for instance, in traditional linear algebra, there are things like the Johnson-Lindenstrass theorem, which says that you can, if you encode things as vectors in high dimensional, in n-dimensional space, of course, you cannot find more than n linearly independent vectors. But if you accept almost linear or almost orthogonal, you can squeeze much more representations into the space.
Mm-hmm.
And also the probability of two high-dimensional random vectors is very high that they are almost orthogonal. Not quite, but almost. And that leads to has lots of interesting consequences. So I wonder, in tropical algebra, are there some things, similar things that happen that use the structure of the tropical algebra in high dimensions?
Mm-hmm. Yes, I understand. So you were referring to does, for example, tropical algebra in high dimensional compare to linear algebra?
For instance, or if there's something particular interesting thing that happens because they have these this structure.
Yeah, I think that's a good question. So I don't know anything related to in tropical algebra, anything related to the result that you mentioned from linear algebra. So yeah, so personally, I don't know any type of this relation that you mentioned.
Okay.
But there might be something related, maybe because this tropical geometry, I think it's quite a big field.
Yeah.
And so other people or more experts in this field, maybe they know some types of things that I don't know.
So I suppose it's an actively developing field right now.
Exactly, yeah.
Okay, thank you.
I can take a quick one maybe. So specifically, I was thinking of the relation between the number of linear regions and things like pooling layers. I would assume that if you have a pooling layer in a CNN, it would, I'm guessing it would impact the number of linear regions and also the number of these tropical regions as well. Is that correct, or?
Yes, exactly. So that's a very good question. So we also intuitively, I think we also, I'd also think that pooling layer should impact, yeah, the number of linear regions that you have in these networks, because I mean, you have this ReLU activation, and from that, normally ReLU activation splits up your input space. If you just have a single activation, this splits it up into two choices. You can either be activated or not. And then for a max pooling, depending on the size of the window, you've got, for example, if you've got a 4x4, 4x4, I mean, or 2x2 window, if you have a 2x2 window, you've got 4 choices, each of which could be maximal. And so I would also think that this should affect the total number of linear regions. Yeah, and using max pooling or something like that should increase the number of linear regions.
Okay, thank you.
What is the time complexity of the tropics algorithm?
That's also a good question. Thank you for that. So in general, it's just 2 forward passes through a network. So one forward pass for the algorithm itself, and then another forward pass for computing the activation patterns that we need in the algorithm. So yeah, so it depends, of course, on your network, but it's yeah, 2 forward passes through the network architecture that you have.
But then you also do some processing on the activations, I suppose.
Yes, you mean you mean, for example, for the activation patterns?
Mm-hmm.
Yes, and that's one of these forward passes. So for each data point that you use, so for example, you've got let's say 60,000 data points, then this corresponds to 2 forward passes through a network. Okay. So one of them for because you need to compute these activation patterns, and then once you've got the activation patterns, you also need to then, starting from the end of the network, you also do all these the operations, but in a reversed way, which is also the same as 1 forward pass through a network.
And so the extracted network, it you mentioned in future work that you could see this as pruning. Isn't it pruning? Isn't the result a smaller network?
Yes and no at the same time. So it's so you've got that the result is something which is so in the result you've got something that a function which can be represented by a neural network, and it has much fewer linear regions. So in that way you could see it as pruning. But then there's not normally in pruning you would like to have a representation of the network which is more compact, and our function that we get is not more compact than the original network. And because then now for each data point that we use during the extraction, we need to store one linear term, and this is quite a large representation of this function. So you wouldn't be able to directly use our method for doing pruning, and yeah, thereby getting some type of smaller representation.
Okay. So Alexis has put a question in the chat. Mm-hmm. Perhaps you would like to read it, or I can read it out loud.
So Alexis asked, asking in text because of sounds in my background, I was wondering if tropics or more generally the conclusions in the paper apply to leaky ReLU as well, and or perhaps some other activation functions as well. If not, could one generalize the methodology to be applicable, e.g. to leaky ReLU? And yes, the algorithm can be used on leaky ReLU as well, and any type of piecewise linear activation function. And for some of the experiments, we've also tried them out instead of with ReLU with leaky ReLU. But when we used leaky ReLU, we didn't notice any difference as compared to ReLU. So we couldn't see anything which was looking differently.
Thank you, Martin, and thank you everyone for attending. Next seminar is in 1 week from now, April 7th, when Jiangyang Zhou is visiting us he's an associate professor at NYU, and he's done some groundbreaking research in neural networks for natural language processing, such as the gated recurrent unit and attention-based machine translation. And so he's going to talk about some properties of autoregressive neural models, which is referred to as oversmoothing. So that's next week. I'll come back then. And thank you for today.